Welcome back to my project. This is Eric. Now we can see microcontrollers based on RISC-V around us. Several companies have now started producing and selling development boards and chips, and many are looking forward to it. When I was a student, I remember studying CISC and RISC architecture. In the case of RISC, small logic is sufficient, but in the case of CISC, large logic is required due to the complexity of the processes that run for each instruction. Anyway, the era of RISC-V, which is more advanced in RISC, has arrived. The advantage of RISC-V is designed to reduce clock cycles per instruction by simplifying the instruction set, so it operates with low power compared to other architectures. Also, it's the use of an open source instruction set. This means that RISC-V is license-free and royalty-free, so it can be used by anyone to run, develop, manufacture, or sell RISC-V chips and software. Because of these advantages, many MCUs based on RISC-V will be launched sooner or later. Okay, so far so good. What I'm curious about is this. Assuming that the same work is done at the same clock speed, the question is whether RISC-V has better efficiency. ESP32 is already a low power processor and can reduce a lot of power consumption by adjusting the clock speed or using sleep mode. What difference does it make in actual use? Here is my ESP32-C6. Compared to other MCUs from Espressif, this supports 802.15.4 radio connectivity, enabling Thread and Zigbee communication. It also supports Wi-Fi 6 and allows you to make Matter accessories. It's like an all-in-one device. Cool. In addition, if only Wi-Fi 5 GHz was supported, it could have been a better MCU. Maybe we can look forward to the next version. Anyway, first of all, this is a single-core MCU based on RISC-V, not extensor. It has two USB-C ports here. It says ESP32-C6 sample chip version 0.0. Perhaps this board will be upgraded in some cases. Also, this board has a jumper on it. According to the document, it's used for current measurement. Here's the ESP32-S3 dev kit C. This dev kit is based on extensor architecture and works as a dual core. If you are starting a project for the first time, I recommend this S3 dev kit. Most projects can be started with this. What will be the performance and hearing result of doing the same task at the same clock speed with S3 and C6? It will add and subtract integer numbers and double numbers a million times. As you know, the S3 can run up to 240 MHz, but I've lowered it to 160 MHz here. So both MCUs have the same clock speed. The result is very interesting. This is the amount of time spent calculating, so the rest the better. I thought the S3 would be overwhelmingly faster in every way, but the results, as you can see, are fast only for real number calculations. This is a natural result. S3 supports a single precision floating point unit. Since the FPU can be accelerated at the hardware level, the S3 is overwhelmingly faster in this area. However, the C6 shows faster performance at the same clock speed for general integer calculations. That's pretty cool. This time, I measured the temperature in the ideal state. S3 is on the left, C6 is on the right. The hottest part on each board is a regulator, so don't worry about it. In the ideal state, the temperature of the MCU seems to be around 20-21 degrees Celsius. It doesn't differ very much. Let's take a look at the temperature change when the MCU is fully loaded and working. The use of Wi-Fi consumes a lot of power. Looking at the datasheet, using Wi-Fi consumes a lot of current. The peak power consumption of C6 is higher for the same 802.11b mode. Instead, you can see that the peak power consumption is the smallest in AX mode. If possible, it will be best to use Wi-Fi in AX mode in C6. In this test, the MCU continuously transmits 1500 bytes of data to the local server through UDP. This can be a heavy task for the MCU, and over time it will heat up itself. Let's see how far the temperature can go in extreme operation. They are both running at the same clock speed and both seem to start as similar temperatures. They are still working on sending data to the server via Wi-Fi, so it'll get hotter and hotter. Currently, both are connected in 802.11n mode. Let me play this video more quickly. Let's look at current consumption for a moment. I wish I could draw a graph of power consumption, but I don't have such a tool yet, sorry about that. I couldn't find any significant difference while looking at this. Both devices have a similar peak power consumption and heating is also similar. If I compare it to x86 or ARM, I think RISC-V will show pretty good power efficiency. However, my short conclusion is that RISC-V's MCU is not much better than general low power MCU. I think ESP32 is already showing good performance while operating at low power. This is a test using two ESP32-C6, one for write device and the other for switch device. Simply, the built-in LED of the write device can be turned on and off via switch device. This demo example is included in ESP IDF version 5.1. You can run the minimal part about connecting 2 gigabits. Today's video ends here. Thank you for watching. See you on the next project.